Okay, welcome back. Today lecture we are going to learn about some basics of the very simple method of the FEM. For example, in the spring element, we are going to learn about the definition of the stiffness method first. So that until previous lecture, we learned about the very simple introduction of the FEM method and then their applications. However, in this chapter, we are going to learn about the basics theory about the FEM method using the spring element. Today's our learning object is first we should define what is the stiffness matrix. Our final goal to make those kind of very simple relationship. In here, F is a force, and then U is a displacement, and then accordingly the K is we are call it this is a stiffness matrices. However, you can easily expect it in the, let's assume that we have a simple spring element or spring system. In here we say that this is a spring constant. However, to describe this physics phenomena using the FEM method, this spring constant must be changing some matrix form. So that in here we are going to learn about how we can make this spring constant as a matrix form. And then after the designing the stiffness matrix, actually local stiffness matrices, we should assemble our real physics system has a series of those kind of spring elements, so that we should assemble this stiffness matrix to the global stiffness matrix. Unfortunately, this stiffness means that local stiffness matrix, we are going to call it as a local stiffness matrix, and then assembled stiffness matrix, we are going to call it the global stiffness matrices. So that to assemble this local stiffness matrix into the global stiffness matrix, we have several methods. The first method is a direct stiffness method. It's a very simple method. And then the other thing, I think the potential energy approach method is a more general method, but it contains some physical meaning than the direct stiffness method, so that to easily understanding what is the potential energy approach method. So I think that in this chapter we are going to learn about both two methods. Let's hear. If let's assume that we have only single element. This element is consist of some solid object. Bar or other, assume that we have some solid structure. However, we are going to say that this solid element consists of some spring element. So I already told you that this spring element can be described as some stiffness matrix form. However, finally we are going to say that some force is equal to the multiplication local stiffness matrix with some displacement. So that sometime I'm going to notate using the notation as U, or in the textbook they use also D. However, this U and D is similar notation. Please do not confusing when I use notation U or sometimes notation D. So that here where the K is related to the nodal displacement, K is this is a wrong description. This is K is a stiffness matrices. D is a nodal displacement, and then F is a nodal forces. So that due to we are going to say that this K is a matrix, so that displacement we are going to use a vector form, and then due to the resultant, so that force is also a vector form. So element is looks like this. Yeah, if it is a single spring element, so in the next slide we can assemble those single elements. Looks like this. So yeah, this is a assembled spring element, but just imagine that this is a artificial solid structure, but I'm not sure that we can use this assembled spring element into where. So anyway, yeah, so if we should define the single element stiffness matrix, and then we are going to assemble this local stiffness matrix equation into the global stiffness matrix equations, so that compared to the local and global coordination system, so that in the previous slide the local stiffness equation use small characters. However, yeah, in the global coordination system we are going to use a capital characteristics, or sometimes you are going to use D. Yeah, this is a capital F, means that force vector in the global coordination system, and then capital K is a global stiffness matrix. Yeah, but D is just nodal displacement in global coordination system. So it is because that specific nodal point is always the same, so that we don't need to changing the small one and to the capital one. Yeah, this is more details about the local stiffness matrix. So that to demonstrate more detail, we first define some terms. First term is node. A node is a point at each element. Yeah, in the spring element we have two node point. Yeah, first we can use some index 1, or second one index 2, or some textbook they use some I or J notation. So depending on the situation, you can choose any index freely. So and then this spring shapes, we are going to say that this is a one element. So that in the spring element, in the single element, we have two nodes. So and then each nodal point has each displacement and forces values. So that means that in the single element we have two displacement variable and two resultant force, or some force variable. So we have two force variable and then two nodal displacement. So this must be same with some local stiffness matrix. Yeah, here we can easily expect it over this local stiffness matrix, although we don't learn yet. Yeah, so that let's think about this is a 2x1 vector. Yeah, this is also 2x1 vector, so that the local stiffness matrix must be 2x2 matrix, so we can easily expect it. So let's go to the next slide. Yeah, so in here we are going to derive the local stiffness matrix, which are already known that 2x2 matrices. So that let's start. Yeah, here, yeah, this is a spring element, so that this spring element has a constant spring constant. Yeah, here K. Yeah, let's assume that. And also we are going to apply some external force in the right hand side. Also point 1 can be fixed on the wall or by some clamped. However, we neglected those kind of boundary conditions, so that due to the resultant force, so that the also opposite force are automatically generated. However, in here we can say that from the spring relationship, we can easily say that total force, external force, equal to the spring constant with the multiplication with the this is a delta, is a total elongation. Total elongations. So that to determine to define the total elongation is here. So this U2 is a displacement of the nodal point, second nodal point. So that we can say that the elongation of the almost same U2. However, if we fixed this nodal point 1. However, this nodal point also first nodal point can move or translated. So that means that total length is, we cannot say that total elongation equal to the U2. That means that, so I say that this is a displacement. So this is not the absolute coordination. So we can say that the exact coordination of each nodal point, so that total initial length is equal to the x2 minus x1. So that deformed after the deformed by this T external force, this x2 position go to this new one position. To more easily understand, I prepared new position, and then also first nodal point move to some direction. This x2 prime new coordination is exactly looks like this. And then here first nodal point also move to the new coordination to looks like this, and we minus 1. The exact value is equal to the so that total elongation is looks like this. So that exactly the difference in the displacement looks like this. So that finally we can conclude that the external force is T is equal to the K with the multiplication U2 minus U1. You can easily expect it. And then here, in the previous slide, we have some two external force. One is a real external force, the other is a reaction force. So however, we say that in the first nodal point, we define the F1x. In the second nodal point, we define the nodal force variable. So that in here, these two and F21x has the same direction. However, F1x and reaction force T has a different direction. So that I added minus sign in here. So that we already know that T is equal to the K multiplication U2 minus U1. So that after the embedding T each equation, we finally obtain those kind of force equation here. So that this is looks like a linear algebra equation. We can easily changing these two linear algebra equation in the matrix form to consist of the matrix form, you can say that in here U and U1, and U2, so that you can combine this into the displacement vector form, and this left hand side you can easily transform the vector form, so that remaining part, here this K U1 minus K U2, so that this is the same in first equation, and then minus K U1 here, and then plus K U2 and here, so that here finally we can obtain those kind of equations, so compared to this, sometimes to express the matrix form we can use the underbar line, so that local stiffness matrix, also K, yes, also K and 1 minus 1 minus 1 and 1. This is a local stiffness matrix of the spring element, so that maybe in the textbook chapter 3 and 4, we are going to learn about the truss element and beam element. Depending on your physical system, we are going to newly define those kind of local stiffness matrices very easily. This is a way to how to derive the stiffness matrix by directly. So that until now, we are going to call it this local stiffness matrices. In Korea, the 국부 강성 행렬. So that please memorize those kind of terms more details. So that this local stiffness matrix has some specific characteristics. First characteristic is symmetrics. So symmetric means that in the off-diagonal terms, this part has the same values, and then this also square matrices. And also, very important characteristics is singular matrix. Singular matrix means that they have this matrix has a lower rank matrices compared to the size of the matrices. That means that in the engineering mathematics, we learned about this matrix. If the rank is below to the 2, this matrix become a singular matrix. Or singular matrix means that they don't have inverse matrices. So that those kind of in the solid structure system, when you define some solid structure as a local stiffness matrix equation, so that or after the assembling the global, both the global and local stiffness matrix become a singular matrix. It is because that let's assume that simple linear algebra equation. How can we obtain what is the final goal of this equation? Local stiffness matrix is a system of the solid structure, and then we are going to apply some external force into the solid structure. So that means that we want to calculate the displacement of the nodal point of the solid structure. So that means that finally we are going to use those kind of relationship. So in here, this local stiffness matrix may be singular matrices. That means that we cannot obtain. This is an unknown variable, and then this is a undeterministics. Or in Korean 부정, or sometimes 불능. What is the 부정 undeterministics? The solution could have an infinite set of the solution. This is the means of why this has an infinite solution. Let's assume that some spring element again. I applied T. However, due to the reaction T, yeah, you can say that, yeah, my first question, this spring element is on the specific point or can translate to anywhere, yeah, without boundary condition. Yeah, boundary condition. What is the boundary condition? Yeah, sometimes we say that u1 must be equal to 0. Without those kind of boundary condition, it is hard to say that this spring element is on the stop condition. Yeah, this spring element always move without any acceleration. Yeah, these forces are equilibrium. That means that total acceleration always equal to 0. However, their initial velocity. Can you say that this spring element is on the stop condition? I mean that velocity is always equal to 0, so that we cannot say that. So that without those kind of boundary conditions, this spring element can translate it. So that means that total displacement is u1 and u2 is, we cannot say that specific value. Maybe the u1 becomes some v0 t equal to the specific value. So that without those kind of boundary condition, the displacement always can have a infinite set of the solution. So that means that to obtain the undeterministic solution, local stiffness matrix must become a singular matrices. So yeah, so similarly, all dynamics equation or fluid dynamic equations, you can use the finite element method. After the discretizing those kind of equation into the FEM form, the all local stiffness matrix or global stiffness matrix will show the singular characteristics due to those kind of region. So that, however, after the applying boundary condition into the local or global equation, that this become a non-singular matrix. So that let's go into the detail. Here, I prepared the two spring system. First spring is attached on the wall, and the other is attached to the other springs. So the first node is fixed on the wall, and then we are going to apply some force at third node and second nodal point. So it looks like this, and then so this capital F means that global forces. So before we start more detail, we can consider those kind of local stiffness force vectors, and then however, I strongly suggest the node index is a more good choice, better choice. However, so that to understanding the here, so we are going to use a local coordination index. So and then nodal displacement also looks like this. However, this is a first element, this is a second element, so that please add those kind of upper characteristics. And the second element, spring element, we also have a similar, this is a, we should use this one 3, and then this one 2, so that here, but this is a second element. So all force and displacement direction is same. This is a local axis coordination, this is a global axis coordination. It's slightly different, but in the one-dimensional cases you can neglect this one. So in here, we can easily, this spring constant K1, you can easily obtain those kind of local stiffness matrix. So that K1 minus K1 minus K1 K1 and then U1 and U3. Yeah, here, so that you can similarly obtain it. I prepared those summarized result here and here. Yeah, however, in the middle nodal point, exactly node 3 has some compatibility condition, so that at each nodal displacement must be equal to same, so that in here we can changing the displacement to U3 become the just U3, and U2 also become a U2, or U1 and U3 must become their own local global coordination system, so that at this stage when you apply those kind of continuity or compatibility condition, you can neglect at this time. So that, and then we have one more some assumption. Yeah, first assumption is let's check some pre-body diagram. Before we I think that in here, let's think about some nodal pulse equilibrium at node 1. We assume that global nodal pulse is the right hand side. However, in the previous element, we normally define those kind of local pulse variable, and maybe in here we also define those kind of pulse variable. However, in the point of nodal point, so that it feels like those kind of resultant force. Just assume that when you apply those kind of force in the right hand side, this nodal point feels some left hand side resultant forces. So that at nodal point of view, so that total force is global F1x and then local F1x1. At the node 3, so that in node 3 it has two local reaction forces the left hand side, and they have only one global forces in the right hand side. And similar manner, second nodal point also has a local force vector in the left hand side, and to the right hand side that they have global F2x forces. So that at each nodal point they must be in the equilibrium condition. So that means that F1x is equal to the smaller F1x, and capital F3x must be equal to the F3x1, F2, F3x in the second element forces. So combination of the F3x in both elements. So that, and last equilibrium equation looks like this. In here, so how can you assemble those kind of equation? To the vector form. Here, F1x, F2x, F3x. Our final goal is assembled equation. So in here, F1x 1, F3x 1, F3x 1, F2x 2. Here. So, but we already know that this part and this part separately. How can you say that? Maybe K1 minus K1, 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 minus, and then F1x, F3, sorry, not F, U1 maybe first one, and U3 second element, but this must become the 3 by 3, not 2 by 2. However, from the compatibility condition, we can neglect special element indexes. So here, this part, similarly, so this part must become U3, this part must become U2. Although we must write the element index due to the compatibility condition, we can neglect this part. So that to match this result, we should combining K2 minus, but in here I need more spaces, so K1 plus K2. It is because that this is a plus. The remaining parts must become 0. So those kind of way we can assemble the local stiffness matrix into the global stiffness matrices. Yeah, further conveniently, yeah, first part actually, yeah, we can use those kind of thing. Yeah, F1 indexes matched U1, F3x indexes matched U3. However, yeah, in the first element, they don't have U2 related to the equations, so that we can, but to combining easily, I added the U2 variable in here, so that you can expand it 2 by 1 vectors into the 3 by 1 vectors, so that, but also local stiffness matrix can change it from the 2 by 2 matrix into the 3 by 3 matrices. Looks like this. Yeah, this is a more simple one. And then second element also can be described expanded local stiffness matrix looks like this. And then from the equilibrium nodal equation, we can say that F1x, F2x, F3x are the summation of the local stiffness forces. So the final equation looks like this. Compared to the previous slide, I made some mistake in here, maybe 3x and this part 2x. So that this is a same, but we have some different node indexes in here, but the result, yeah, very similar. So that, yeah, corresponding to the U3 and 3 by 3 part, and in previous slide, and U3 part corresponding to this part. So that depending on your assembly, so that we can finally obtain the slightly different shapes of the global stiffness matrix. However, this is a result from the using the different node index order or sort ways. So that's first time I strongly suggest this one is first one, this is the second, yeah, this one is third. Means that, yeah, those kind of bad quality node index result in some different, slightly wrong ordering on the equation. So that, however, those kind of way you can easily combining the global stiffness equation from the local stiffness equation. Those kind of way is a direct stiffness method. So I think it's very simple. So that those kind of way we can combining our local stiffness matrix into the global stiffness matrix. So the final result looks like this here. Yeah, so yeah, again, F is a global nodal force matrix or vector. Yeah, D is a global nodal displacement vector, and K is a total or global system of global stiffness matrices. Normally I'm going to say that global stiffness matrices. So that, yeah, let's check the more details about global stiffness matrix. This global stiffness matrix also symmetric. Yeah, this is the same. And also, yeah, although I don't want to calculate the length or determinant of the K, however, I can easily expect that this value must be equal to 0. Please try it. So that this means that this global stiffness matrix also singular. Yeah, so to obtain the solution of the displacement vector, we need some special boundary condition. So this method is a direct steepness method, so that this method very simple and easy to understanding. So this method is a basic assumption, is a superposition, superimposed to be obtained global steepness matrix is a basic assumption of this method. But this method has some limitation. Each local vector must be extended. But these vectors generally 2 by 1. However, depending on your system, this all local matrix must be extended. So actually, in our point of view, we can easily expand it. However, in the computational point of view, they need several techniques to expand it. So that actually it's not a good way to use those kind of methods. However, you can easily use those kind of direct steepness method. And also, I already mentioned that local steepness equation, especially global or local steepness matrix, is a singular matrix, so that we cannot inverse of this K matrices. However, to obtain some exact solution of the displacement, we need the inversion of this steepness matrices in here. So I prepared some very simple cases. Previous here K1, I assume that K1 and K2 is equal to 1, so that the result and looks like this. Here 2 and 1 0 1 1 0 minus 1. Here. So that using the MATLAB, I check the determinant of the K, so that although I prepared the specific cases of the spring constant always equal to 1, however, the answer is always equal to 0, so that we can easily expect this global steepness matrix is also singular matrices. And then also this, it has a physical meaning. I already told you the structure is unstable. Unstable means that they do not have a specific deformation. In the solid structure, we always learn about how much solid deformed. However, in these stages, we cannot determine this specific value. So that means that this solid structural system must be translated with a specific velocity, so that we cannot determine the exact deformation or displacement of the solid structure. So that means that solid structure has some rigid body mode or rigid body motions. Rigid body motion has the displacement has some time-dependent value, not specific value. So we cannot say that some solid structure has a rigid body motion, mode. Maybe I hope that we can achieve the goal. I think that in the dynamic course, so that we already learned about the mode. It is because that K and U and V, F. K. This is some square, some vector, so that means that we can extract some eigenvalues or eigenvector. So that in here, eigenvector means that eigenmode. So that I think that you guys learned about those kind of system dynamics in the vibration lecture or some dynamics course. So that using the finite element method is strongly related to those kind of work. So that in the end of the part of the lecture, maybe we are going to learn about the mode and then how can we use those kind of mode. So that so let's skip this part more detail. So anyway, please remember that without the boundary condition, so global steepness matrix always singular. So next work is we must apply some boundary condition to obtain the specific value, specific deformation. So that we have two different boundary conditions. First is a homogenization boundary condition. The other is a non-homogeneous boundary condition. Homogeneous boundary condition means that their displacement equal to 0. Non-homogeneous boundary condition means that they have a non-zero value. In the previous example, we had those kind of solid structure. This part, displacement always equal to 0. This means that this is a homogeneous boundary condition. This U2 and U3, they don't have any boundary condition. This two value is unknown, and we want to need solve. Solved. Must be solved. So anyway, non-homogeneous boundary condition, non-zero value means that I think that I prepared. No. So I think this first nodal point move to the specific amount of the displacement. So that in here, so that U1 equal to the delta, some specific value, depending on your system. But I cannot imagine that what kinds of the cases you can apply those kind of non-homogeneous boundary conditions. So anyway, so I think that all boundary condition must be homogeneous boundary condition. However, let's first check the homogeneous boundary condition. In the previous example, I prepared those kind of solid structure. I already told you that first node is always fixed. The U1 is equal to 0. Let's think about, we already know that U1 value. So that we don't, this is out of scope in equation. So but in the matrix form, we don't have any idea. Also this matrix is also the singular. So we cannot take any inversion to obtain the U2 and U3 value. However, let's think about the, here, let's rearrange this equation. K1, U1 is equal to 0. 0, U2 minus K1, U3 equal to F1x. Okay. The second equation, 0, 0, plus K2, U2 minus K2, U3, F2x. K1, 0, and minus K2, U2, plus K1, K2, U3, F3x. Here, so U2 and U3 is an unknown variable. We have two unknown variable. Means that we need two equation. So that we have three equation. That means that we don't need first equation. So in here, this is enough to obtain the U2, U3 value. So and also this is a 0. So that we don't need to this part neither. So that I think that this K2 and U2 and minus K3 U3 equal to F2x, and then K2 U2 plus K1 plus K2 multiplication U3 equal to F3x is equal to this equation is enough. So that finally this we can remove these two lines. So and then we obtain the reduced matrices. Stiffness equation, and then we can take inversion. So in these stages, this reduced stiffness matrix is not singular matrix anymore. So let's talk about K1, K2 is equal to 1, K1 is equal to 1, so that this part become 2. let's check about determinant of this matrices. How can you calculate the deterministics? AD minus BC. So that 2 minus 1 multiplication is plus 1. So that is equal to 1. Not equal to 0 anymore. So that this matrix does not anymore singular matrix. So that means that we finally obtained a specific value, displacement value. So if you are not familiar with the linear algebra equation, please review our lecture material or some engineering mathematics or linear algebra textbook. So this is a non-homogeneous boundary condition. So that here, so I already told you that non-homogeneous boundary means that we are going to apply some specific value in the boundary condition, delta. So the spring first nodal point to move to this amount of value. So similarly we can obtain those equation. So however I'm write down this one and this one. 0 delta plus k2 u2 minus k2 u3 equal to f2x, and then here minus k1 delta minus k2 u2 plus k1 plus k2 u3 equal to f3x. So this in the homogeneous boundary condition we can simply delete these two column, row column and first row and second column vectors. However, in here, although first term is equal to 0, so that we can neglect this delta in second equation. However, this part we cannot neglect anymore. So that means that, but in the left hand side we want remains only unknown variables. So that this part is a known variable. It is because that we know that a spring constant, and then we know that specific boundary condition. So that means that this part go to this side. So that means that if you want to reduce this matrix, similarly reduce the stiffness matrix is looks like this, and then u2 and u3. However, this right hand side is not f2x, f3x anymore. So we need a more term here. So that means that this multiplication part, we need this part. Although this part in second term, due to the happy cases, so that we can neglect this part. However, we need maybe exactly minus sign, so that we need those kind of treatment actually. So that if you in the homework, maybe I'm going to give you those kind of non-homogeneous boundary condition in your system, you should carefully check to solve those kind of equation. But if you don't want to use a matrix form, you can simply solve the bilinear algebra equations. But I strongly recommended those kind of relationship. Okay. So non-homogeneous boundary condition must be considered those kind of additional term. Normally we are going to say that this is some arbitrary force, so artificial force, but most of the boundary condition is a homogeneous boundary condition, so you don't need to worry about those kind of boundary condition. But please remember if we applied some non-homogeneous boundary condition on the specific node, at that time we must consider those kind of additional force term. So And then fortunately, this part we can neglect the additional postulate due to some non-homogeneous boundary condition. But yeah, actually, when you use some linear algebra equation, but at that time you don't worry about those kind of things. However, in the matrix form, yeah, FEM method is when we use FEM method, the matrix form has a lot of beneficial advantages. So at that time, yeah, although when we apply the homogeneous or non-homogeneous boundary condition, the local stiffness matrix or global stiffness matrix and displacement vector always the same. However, the vector, force vector, is slightly different. So that, yeah, although, yeah, you think that it's very uncomfortable when you use those kind of method. However, in our final goal is we are going to solve this linear algebra equation by computer. So that when you added some algorithm, you can easily achieve this goal, yeah, simply. So anyway, so this is about some boundary condition. Yeah, next is another method to assemble the local stiffness matrix into the global stiffness matrices. So that, yeah, this is end of today's lecture. So that let's continue in the next lecture. Yeah.